Hi everyone, my name is Qiaori and I come from Huazhong University of Science and Technology. I'm excited to have a chance to introduce our work StripeMerge, efficient wide stripe generation for large-scale Erasure-Coded storage. This is a joint work with the Chinese University of Hong Kong and High Commission. First of all, let's review some basics of Erasure coding. Erasure coding is a widely deployed redundancy technique. Compared to replication, Erasure coding needs much less space, so it can provide low-cost fault tolerance. Take read Solomon codes, one of the most popular Erasure codes example. First, we can make the data divided into k chunks, and then these data chunks are encoded to generate m parity chunks. All these chunks constitute a stripe. Lastly, we distribute them to k plus m nodes. Recently, storage practitioners are interested in further redundancy reduction for extreme storage savings. If we have a very large k, while m keeps relatively small, the redundancy will be substantially suppressed. Here comes the wide stripe. By the way, our previous book, Easy Wide, appeared in Fast 21 a few months ago. Well, we keep thinking about this question, how to generate wide stripe. One natural idea is to generate it directly when the data is first written. But we should take performance into consideration too. Actually, you need to retrieve k chunks to repair the single chunk. So we tend to adopt a tier approach to generate it. Our motivation is that the exact frequency is high at first, but it decreases at the data age. If the original data just entered the system, it is stored in the nanostripes, as it usually has high exact frequency and we don't want the frequent and expensive repair. But when the data age, we can encode it into the wide stripes. Things like a good balance, right? However, re-encoding in the tier generation may need to relocate the data chunks and regenerate the parity chunks. This operation may incur substantial bandwidth overhead in data transfers. And how to mitigate data transfer during wide stripe generation, it is a challenge. Now, we specifically focus on this problem. Two km stripes merge into the 2km stripe. It is illustrated in the figure. So we start to speculate that it is possible to locally generate both data and parity chunks. We found the case as shown below. If the data chunks reside in the different nodes and the parity chunks have identical encoding coefficients and reside in the same nodes, we even do not need any transfers to finish generation. We call it perfect merging. This idea is based on the key insight. The Vandermonde-based articles allow local generation of the new parity chunks by using the old parity chunk as input. It is an important property for wide stripe generation. Okay, before stepping into the details, let's grasp at what we have done. We had first addressed the wide stripe generation problem. We modeled the problem with the bipartite graph, making some formulation and proofs. We designed the StripeMerge, which consists of two heuristic algorithms for the problem. And in evaluation, we can see that our approach really works. The models come first. We formulate the wide stripe generation problem by bipartite graph modeling. The details will not present today, but that's one thing that we can see that when the number of narrow stripes is sufficiently large, zero-cost merging scheme also exists theoretically. Well, interestingly, we found that there's also some gaps between the theory and the reality. Firstly, our problem can be transformed into the maximum matching problem on the bipartite graph, but it is high complexity leads to an obstacle. Secondly, a large number of stripes are required in it, but only a limited number of stripes in practice. Okay, so time complexity seems like a major concern, but how about try it in another way? We decide to start in naive greedy heuristic. We found that actually we can transpose chunks to satisfy perfect merging. Yeah, and then you can get some merging cost of the pair of the stripes. Here's an simple algorithm. You can get merging cost of all pairs and then select the minimal pair of stripes every time. So we can get the stripe merge G. As you can see, the time complexity is lower to big O of k plus n squared. But according to our experiment, it may be time consuming in some cases. So can we further improve the greedy heuristic? Yes, and the parity aligned property is a key. I mean, the parity chunks have identical encoding coefficients and reside in the same nodes. Our main idea is to search in the parity aligned sets in order to rapidly merge a large number of stripes. Additionally, the hash table will allow us to accelerate the construction of parity aligned sets. In this algorithm, we search for the pairs in the parity line sets, select the minimal one in the step one every time, and use stripe merge G to deal with the remaining stripes. You see, the time complexity has been reduced to big O of k plus n and n in the best cases. Here's an example of stripe merge P. It uses 5 steps to get the scheme, but they will not be discussed today. You can find more answers in the paper. Well, let's check StripeMerge performance. As you can see, in simulation, StripeMerge significantly reduced the white stripe generation bandwidth over the state-of-the-art up to 96%. And it still maintains the advantage in experiments. More results of the experiments are presented in the paper. Well, at last, we can make a summary here. In this paper, we propose stripe merge, a novel mechanism that merges narrow stripes to efficiently generate wide stripes. And then we make some proofs and formulations, propose practical heuristic, and in evaluation, our efficiency is shown too. By the way, our source code is available on GitHub now. And that's all for stripe merge. Thanks for watching, and welcome to follow our work.